All right, taking a look at this next example, let's rewrite it as a proper integral first. Okay, now in this case we're going to let a, the lower limit, approach negative infinity. There's a little more involved in evaluating this integral than just kind of reasoning through it. This is an exponential function, so we're going to use u substitution. So thinking about this just right up here, I'm going to let u be the exponent 1/4 x. So in that case, my du is going to be 1/4 dx. So I need to bring in a 1/4, which means I'm going to pull out a 4. So I'm going to kind of scoot over here. You might have more room. Okay, I'm going to keep the integral on this because I'm switching over to a u integral. This is going to be e to the u du. And with that formula, we know that goes back to e to the u. So this is an equals. Okay, integrating back to e to the u, where u was a 4th x. And I think I left off my 4 back here, so I need to bring it on here, 4, and then the 4 goes here too. Okay, let's do the evaluation part. So 4 times the limit as a goes to negative infinity. Oh. Okay, oh, and I need limits here, a and 0. Okay, so plug in 0, e to the 0, that's nice. That'll be 1 in the next step, minus e raised to the a over 4, whatever a's value is. Okay, and I'll come back over here. I think I have a little bit more work to do. Okay. This is going to be 4 times, I'm going to lose the limit here. It's because I am going to plug in a for negative infinity for a. So e to the 0, which again will be 1. Should have written that as 1, minus e to the negative infinity over 4. Negative 1/4 infinity. Okay, so we're going to have to work on that a little bit. If you wanted to, you could rewrite this as a fraction, 1 over pulling the e to the denominator, and I'm going to write it as 1/4 infinity. Alright, and when we think about this right here, well, e to the infinity is super large, even if it's 1/4 infinity. This is a super large denominator, so the value of this fraction is going to go to 0. So my answer is just going to be 4. 4 times the 1. You can confirm it with the calculator. You can type this exponential function into y equals, and then you can evaluate this integral. At least on the 89, I know that there is an infinity key somewhere that you can find and evaluate, and you should get 4. Not real sure on an 84. We'd have to investigate that. Alright, so the bottom example on this page is to let a function be represented by this rational function right here, a rational equation. R is going to be the unbounded region in the first and second quadrants below the graph of this function. And we're going to find the area of that unbounded region. Okay, so I'm going to go ahead and get a picture. I know yours is still there, but I've tried to convert this worksheet to a Word document from a software program, and it just didn't do well with the graphs. Okay, but if you were to graph this rational function right here, it's continuous. Okay, you might think there's a vertical asymptote, but remember, looking at the denominator, there's no way you'll ever get 0, so it's actually something like this. And so we're supposed to find the area of this region, this unbounded region, as the graph travels out that way. and the graph travels out this way. So we can see if it converges or diverges. If we get infinity, then we know it's going to diverge, and if we get a value, it's going to converge. So it'll be interesting to see what happens. Okay. So let's set up the integral that represents that area. So O through L, this is going to be negative infinity to infinity. So this is that third and final example up there at the top of this page. Okay, so let's write it proper. So first of all, using properties of integrals, we know we're going to go from negative a to some c value. Well, I think what I'm going to do is I'm going to choose my c value to be 0. And then I'm going to add the integral from 0 to positive infinity. Okay, both of these are improper, so I'll have to rewrite them as proper integrals. So the limit as, I guess here we'd say a goes to negative infinity, and then from a to 0. Plus, it's going to get kind of crowded. I guess I didn't plan that graph too well. Let's make this a proper integral. Oh, I need some space here. So let me take that away and leave some space. So this is going to be the limit as what? Let's see, b goes to infinity. Positive infinity, yeah. This would be 0 and this would be b. Okay, so we have our work cut out for us. Let's see down here. Okay, so now I'm working on this part of the problem right here. If we think about it, it's just going to require us to go back into our memory. This is actually the arctan integral. This is 1 over 1 plus x squared, just rewritten in a different order. So yeah, this is arctan. Okay, so limit as a goes to negative infinity. The antiderivative of 1 over x squared plus 1 is arctan, inverse tangent, however you want to see it. Arctan of x, and we will evaluate from a to 0. And this is also arctan of x. Just thought I'd write both notations here. 0 to b. Okay. Yep. Now I'm ready to evaluate here. So I still have the limit. I just still have to do the evaluation part of the FTC. Trying to write small here. Arctan of 0. I think I'm going to go to the -1 symbol here just to save some space. Minus arctan of a. Plus, working here, arctan of b minus arctan of 0, or inverse tangent of b minus inverse tangent of 0. Hopefully everything's in order there. Okay, I'm going to wrap it back down here to the left in case I need more space. So now I'm here. Okay, what angle has a tangent ratio of 0? Alright, so I'm going to do a little cleanup. So keeping the limit, I'm not ready for that yet. Okay, so the angle whose tangent is 0 would be 0 minus arctan of a. So I'll be plugging my negative infinity in here in just a second. Minus the limit as b goes to infinity of arctan of b minus, and that'll be a 0. Okay, this was just kind of weird. Coming back here to evaluate now the limit, I'm going to plug in negative infinity for a, so I can lose the limit statement, and this 0 right here I just won't write down again. Okay, so I'm trying to think, alright, well, what is this limit when I plug in negative infinity for a? Well, that requires our knowledge and understanding and our remembrance of what the arctan graph looks like. So I'm going to come up here, and I'm just going to real quickly remind us what the arctan graph looks like. Okay, you could dig back into your notes, and right before we found derivatives of inverse trig functions a little bit ago, I provided you with a worksheet that had the 6 trig graphs and the 6 inverse trig graphs. So that one was there, but just real quickly to call it back up for us, the arctan graph has a range from negative pi over 2 to positive pi over 2. They actually serve as asymptotes. We put little dashed lines here. Okay, and our arctan graph comes in like this and then like this. Okay, so it's one of the regular tangent periods reflected across y equals x. All right, and that might help us now when we come back down here. Okay, so this is saying as a goes to negative infinity, so the arctan of a, or negative infinity, minus, now let's find this one, the arctan of what, positive infinity, is going to give us our answer. Okay, so let's see where we're at. Okay, on the graph, as you go to negative infinity, as I go to negative infinity, what are the y values approaching? Well, that's going to be negative pi over 2. Okay, and so I think I forgot my 0 over here. I did, didn't I? So this should be 0 minus, so this should be minus here. I knew that was going to be positive. So this is the opposite. Okay, so I'm going to have the opposite here of negative pi over 2. That negative coming back from here where I had the 0 minus. Okay, and then I have minus. Hoping that one's right, okay. And so now what is the arctan of infinity? As I go to infinity, my y values are going to positive pi over 2. Okay, so now again I see that this should have been a plus. Don't know if it was a plus and the pen just took away my plus, or if that was me, but I'm adding these two limits here. So this was a plus here, coming back over here. This is an addition sign 2. This is an addition sign 2. Alright, so finally, the opposite of negative pi over 2 plus pi over 2 results in a whole pi, and that is our answer. So we would say that this improper integral actually converges, and the area is pi. Okay, so looking at the time here, I think I better cut this video off because I do want to look at page 3 with you. I know there's only 2 examples, but those are both pretty involved, and it probably will take another 15 minutes just for those 2 examples. So I'll see you in just a second.